All right, we are going to look at some ways that you report data now, and when you see data in the news, what you might think about it, okay? So again, we have talked about the words population and sample. You know that population means the entire group or objects that you're selecting from. Sample is your subgroup. And then we need to talk about two new words, parameter and statistic. Parameter is anytime you see a number reported about the entire population. If it's about the entire population, then it is a parameter. Sometimes it's what we want to find out about them, and sometimes it's what we already know about them. But either way, if it's about the population, it's a parameter. If it's about just a sample or a subgroup of the population, then it is a statistic. Okay? So here's some examples. 20% of Americans have high cholesterol. A survey was taken of everyone who went to the doctor last week, and 25% of them had high cholesterol. So there's two numbers there, 20 and 25%, and you need to determine whether those numbers are a population parameter or a sample statistic. Okay? So 20% of Americans. So that's all Americans. That would be a population, and so this 20% would be a parameter. And then the 25% is a result of people who went to a doctor last week. That was a result of a sample or a survey. And so because it's a result of a sample, that would be a statistic. All right, in the next example, every fifth person in the lunch line, so again, that's about a sample of a population, had a cell phone. 91% of them had one. And then 89% of all Hutchinson High School students have phones. So this 91%, because it's a subgroup only about the people in the lunch line, every fifth person in the lunch line, this is a sample, or a statistic, sorry, a result of a sample. It's a statistic. And the 89% of all of Hutchinson High School students would be about the population of Hutchinson High School, and so that would be a parameter. Okay, do samples always give us good data about a population? And we'll talk about this in general. But suppose that in fact, unknown to Gallup, you've probably heard the word Gallup. They publish a lot of polls that they do. But anyways, unknown to Gallup, exactly 60% of all adults have bought a lottery ticket in the past 12 months. Since Gallup didn't know that fact, they conducted two studies to determine the number of adults that have actually bought a lottery ticket in the last 12 months. Okay, and I'm going to just kind of show you some results so that you see what happens. In the first study, they randomly chose 100 people at a time to sample. And they did this over and over and over many times with different groups of 100 people. And the results were quite varied. Oftentimes, that sample of 100 people answered really close to the actual 60% of people that bought a lottery ticket. However, many times the sample was quite a bit over that 60% or under that 60% of people that we know actually bought a lottery ticket. So what this graph shows you is they sampled different groups of 100 people many times over and over and over and over and over again. Okay? And lots of those times, those samples of 100 people were really close to 60%, but they had several groups of 100 people that were way off that 60%. Many groups that were way off that 60%. And that's what happened when they sampled groups of 100 people at a time. Then they repeated the study, and this time, instead of grouping 100 people, or sampling 100 people, they chose 1,523 people to participate in their study each time they did it. And they did that over and over and over again. 1,523 people each time they surveyed. And when they did that, they got results that were much closer to the actual 60%. They still had some groups that were a little bit over 60%, and they still had some groups that were a little bit under 60%, but most groups were pretty darn close to that 60% of the population that has bought a lottery ticket. So you can see that the more people you sample, the more likely you are to be closer to the actual truth. Okay? Sometimes you're going to grab a group of people, and for whatever reason, they're not going to represent the population. You get just a fluky group that's overrepresented or underrepresented in some group, and it throws it off. But if you choose a big enough sample, you should get results that are pretty darn close to the actual truth about a population. Okay, when you use samples to estimate something about a population, there will always be some error, always. If you're only choosing a subgroup, it is never going to perfectly match the actual population. But the bigger the sample, the less the error. The bigger the sample size you use, the closer you are to getting to the actual truth about an entire population, even just if you pick a subgroup. All right, but there is always error, and we refer to that error as margin of error. And we use the formula 1 over the square root of n. N is the sample size, meaning if you sampled 5,000 people in your study, then n would be 5,000. If you sampled 500 people in your survey, 500 would be your n. Okay? 95% confidence level. We will talk more about confidence levels in a minute so that makes sense. But this is the formula we use for a 95% confidence level, and I'll tell you what that means in a little bit. But this formula is for the 95% confidence level, which we will stick with here in this part. If we were doing AP stats or other stats, we would use some different confidence levels and different formulas, and we'd talk about that. But in this class, we're going to stick with that 95% confidence level. Okay? When you report margin of error, the MOE, it is rounded to the nearest percent. So if your margin of error comes out to be 5.5%, you're going to have to round it to 6%. If you want to decrease that margin of error, what you're going to need to do is you're going to need to take a bigger sample. Okay? So that is the only way to decrease your margin of error. And you need to know that it is determined by sample size, not population size, but sample size. The bigger the sample, the closer you will be to the actual truth about the population, even if the population is really big. Okay? All right, so we're going to look at some different sample sizes, and we are going to calculate their margin of errors. So we'll start with a sample size of 100. To do that, you're going to take 1 over the square root of 100, and then times 100 just to convert it to a percent. And when you do that, you get 10%. It gets rounded to the nearest whole percentile, so I actually don't need to round this one, but it would get reported as 10%. Okay? 200, I would take 1 over the square root of 200. Times 100, and I would get 7.07%, but it gets rounded to the nearest whole percent, and so it would get reported as 7%. Sample size of 400. I think you guys are seeing a pattern here. And that is 5% and does not need to be rounded because it's already there. I will tell you that you can check your sample size of 1600 and sample size of 2500. But this, you would get 2.5%, which rounds, of course, to 3%. Oops. And then here you would get 2%, which, of course, gets still reported as 2%. Okay, so if you look at this, I want you to think about how do you cut a margin of error in half? Well, if you look at this, if you compare a sample size, let's say, of a margin of error that's been cut in half, okay? So this is 10% right here, this is 5% right here. The margin of error has been cut in half, but the sample size had to go from 100 to 400, so it was a 4 times bigger sample size. Okay, so that's what you do to cut it in half. How do you cut a margin of error in thirds? I think you can figure out that the margin of error formula has a square root in it, and I want you to notice the square root of 4 is 2, and that's why in this last example I had to take a 4 times bigger sample size. So if I want to cut that sample size in thirds, I'm going to need to take a 9 times bigger sample. And then to cut it in fourths, I'm going to need to take a 16 times bigger sample. Okay. All right, so this is important to know here. A margin of error of plus or minus 3% means, and you guys can read this, but it means if we took many, many samples using the same method we used to get this one sample, 95% of the samples would give us a result within plus or minus 3 percentage points of the actual truth about the entire population. Like I said, every once in a while, you are going to grab a group of people and total fluke chance, but when you randomly drew your people, maybe you got lots of girls in your sample. Or maybe you had hardly anybody with money in your sample. Or maybe you happen to have all old people in your sample. Or whatever. But for whatever reason, some fluke thing happened where you randomly drew, just by chance, a really odd sample that did not represent your population really well. 95% of the time, that's not going to happen. 95% of the time, if we use the same method we did, we're going to get a good sample, and it's going to be pretty darn close, within 3% of the actual truth of the population. But there are going to be times when you're going to, for whatever reason, randomly grab a weird group of people that doesn't fit the population, and your results are not going to be real close to the truth, okay? And that's what margin of error is referring to. All right, here's another example. If you do one survey where you sample 500 people out of 2,500, and you do another survey where you sample 500 people out of 10,000, which survey will have a larger margin of error? And people tend to think the second sample will have a larger margin of error because they used proportionally less people in the population. They used 500 out of 10,000 versus 500 out of 2,500 people. But you need to remember that sample size is not determined by the population. Margin of error is determined not by the population but by the sample size. And so, if I were to calculate the margin of error for both of these, in both cases, I would go 1 over the square root of 500 times 100, and either way, I would get the same margin of error. And so, the margin of error would be the same because it's the same sample size. The population does not matter. It's the sample size that matters. Okay? All right, and then we're going to talk about confidence statements. These are things that confidence statements need to include. And again, we are always going to use the number 95% confident in our class because of the formula that we use for margin of error. You can use different confidence levels. If you use higher confidence levels, you will have a higher margin of error automatically. And that's really the only thing you need to know. Higher confidence levels come with higher margin of error. And here's why I say that. Let's say that I was giving a test. And I say, you know what? I think Billy Bob can get 99% on the test. And I think Susie Q is going to get 95% on the test. Okay? Well, the chances of someone getting 99% are much harder to obtain than the chances of somebody getting 95%. So you have to leave yourself more room for error when you leave a higher confidence level, okay? So again, if I say that I'm 99% confident, I am more likely to be wrong than if I say I'm only 95% confident. The chances of that actually coming true are more likely than someone who has to get 99. Okay, so that's why higher confidence levels have to come with higher margins of error. Again, we are always going to use 95% in our class because that's the formula we'll use, but here's sort of the standard form for a confidence statement, okay? We always start out with, we are 95% confident, and then you always tell me what we're talking about, what's our study about, and then you give me the results, and you give me the margin of error in it, okay? Okay, so here's an example of a study that was done, and if I want to report the results of this study, I am going to do it in one sentence that gives me sort of all of the information that I need about this study. Okay, so here we go. This study was done by the Mayo Clinic, and they wanted to figure out how many females between the ages of 42 to 50 had had a mammogram in the last 2 years, and they did a survey, and they surveyed 300 people, and 123 of them had had a mammogram in the last 2 years. All right, so the first thing you want to figure out is what was the population? What group of people are you wanting to know something about? And in this case, the people I'm wanting to know something about are females, ages 42 to 50. The parameter is, what are you going to find out about them? And I want to find out what percent of females had a mammogram in the last 2 years. The sample would be how many people participated in your study. What was the subgroup? How many people were in that? And there was 300 of them. And again, they were all women, ages 42 to 50. The statistic is the result, and in this case, 123 out of those 300 people, which if you figure that out, it comes out to be 41%. The statistic does not need to be rounded to a whole number, so if it came out to be 42.56%, you may report 42.56%. This one does come out to be a whole number, so I'll obviously leave it there, but you don't need to just round the statistic to 2 decimal places. The margin of error, again, you're going to go 1 over the square root of the sample size. In this case, the sample size was 300. And that becomes 5.8%. But of course, margin of error gets rounded to the nearest whole number. And so I would report that as 6%. Okay, and then here's kind of the little formula you use for confidence statements. You're always in this class going to start out with, we are 95% confident that the percent of, and now tell me who you're talking about. Again, in this case, it's women, ages 42 to 50, that, in this case, had had a mammogram in the last 2 years, is, and then you're going to give me the statistic. In this case, it was 41%, plus or minus the margin of error, which is 6%. And then you're going to add and subtract those two numbers. So 41 minus 6% is 35%, and 41 plus 6% is 47%. Okay? And that's sort of the little formula you're going to use to report your confidence statements every single time you do that. Okay?